Okay, so we're going to have a look at AS and A2 redox chemistry, and this is really just confined to assigning and using oxidation numbers or states, and then writing balanced redox half equations and then turning those into full redox equations. So if we just remind ourselves first of all in terms of redox, oxidation is when electrons are lost, and this can be represented by an increase in the oxidation state, the oxidation number. And reduction then is when electrons are gained by something, and this is represented by a reduction or a lowering of the oxidation state of that thing. So bear that all in mind. Okay, you within your notes will have a list of rules. Okay, it probably looks something like this. Okay, for assigning these oxidation numbers and states. What I'll do is I'm going to work through each of these, giving a sort of an example of how each works, and hopefully by the end then you should be able to do any question that crops up in terms of assigning an oxidation state to an element within a substance. So I'll work through each of those examples and then I'll do a few additional examples. Okay, so rule number 1 here states that the oxidation state of an uncombined element is 0. And if you think about what I said about gaining and losing electrons, well that would make sense, because an element uncombined on its own has neither lost nor gained electrons, so it has an oxidation number of, in this instance, as we've said, 0. Okay. Now that doesn't matter whether it's diatomic, triatomic, polyatomic, whatever. So for example, chlorine on its own, uncombined, has an oxidation number of 0. Sulfur, uncombined, on its own, has neither lost nor gained electrons, and also has an oxidation number of 0. So all those are uncombined elements, 0. The rule number 2 then is that an atom in a monoatomic ion has an oxidation number equal to the charge. So when we talk about monoatomic ions, we're talking about, for example, iodine in an iodide ion, and it has an oxidation number equal to the charge, so it's -1. Oxygen, of course, 2- has an oxidation state of -2, and magnesium is a 2+ ion and has an oxidation state of +2. Okay, so very simply, okay, aluminium 3+ has an oxidation state of +3. Okay, so those are again very, very simple. Okay, the next rule number 3, the sum of the oxidation states in all the atoms in ions of a neutral compound are equal to 0. So sometimes for these we would need to know the rules of perhaps some other things within here. Okay, so let's take for example carbon dioxide. So that's in a neutral compound. Now, we haven't come across this rule yet, but oxygen is always -2 except when it's with fluorine, so it's -2 in this instance, and there's 2 of them, so it's a total of -4. The rule said that the sum of the oxidation states was equal to the charge, which is of course 0 in this one. So therefore the carbon, there's only one carbon in here, must have an oxidation state of +4, because +4 plus the -4 gives us 0. Okay, if we took let's say chlorine, okay, in this compound again it's a neutral compound, so all the charges will add up to 0. Oxygen is again -2, but there's 7 of them, so it's -14. So you've got 2 chlorines, -14 equals 0. So each chlorine in this instance is +7. Okay, now you might say, well, how do I know oxygen is -2? Well, we'll look at some rules later on which tell us certain elements are always in the same oxidation state. Okay, right. The next one then is the sum of the oxidation states of all the atoms in an ion are equal to the charge on the ion. So let's take a sulfate ion, I suppose. Would be good. So the sum of all the oxidation states is equal to the charge on the ion. The charge on the ion is -2. So the sum of all the oxidation states are equal to -2. So it's 1 sulfur plus 4 oxygens, 4 oxygens, each of which are -2. Equals -2. So the sulfur therefore must be in its +6 oxidation state, because +6 -8 equals -2. Sulfur in this scene is in its +6 oxidation state. If we then had a look at, let's a sulfite, an SO3 2 minus, just to show that sulfur can have variable oxidation states. So sulfur 1 sulfur, plus there are 3 oxygens, each of which are -2, equals the charge is -2. So this time sulfur must be in its +4 oxidation state. If we look at chlorine, for example, put it into this. Okay, so chlorine, so 1 chlorine plus 3 times -2 equals -1. So therefore chlorine must be, in this particular instance, +5. Okay, so hopefully you've got the concept there of to where we go from there. Next one then, the more electronegative element in a substance is given the negative oxidation state, and the less electronegative element is given the positive oxidation state. So this might apply if I have, the rule for oxygen is that it is usually -2, but in this instance it's with a more electronegative element, fluorine. Remember, electronegativity increases in the periodic table from bottom left to top right. So it cannot be -2 anymore. Fluorine is the most electronegative element and is always -1 end of. Okay, there are no exceptions for fluorine. Okay, so you have 2 fluorines. Okay, so in total it's -2. So this instance, the oxygen in it is in its +2 oxidation state. Okay. So some elements always have the same oxidation state no matter what they're in. There's a couple of exceptions. So if we look at them, group 1 is always +1 and group 2 is always +2. But hydrogen is also always +1. So what happens if I have hydrogen attached to a group 1 metal? Well, group 1s are always +1, and if you say here it says hydrogen is always +1 except in a metal hydride. Well, here it is in a metal hydride, so it must be, the total charge on that is 0. So the hydrogen must be -1. Okay, this time we have oxygen. We've already looked at the exception for oxygen in terms of fluorine. Okay, where F2O it becomes, we said earlier, +2, but also in peroxides. Okay, so we might have something like H2O2, where hydrogen is now in hydrogen peroxide. So hydrogen is, or oxygen is now in a peroxide. So the hydrogen is +1 times 2, so it has a total contribution of +2. The overall charge is 0. So therefore each oxygen must be -1. Okay, equals 0. So this time oxygen, instead of being -2, is -1. Okay, right. So that, guys, is how we work out oxidation states and assign them to individual atoms within elements. So if we look at a couple of other examples perhaps, and I'll just do a few, and then there's some in your notes which you can maybe have a go at. So if we took a look at, let's say, applying our rules to ammonia or nitrogen, we're looking for nitrogen, so the overall charge is 0, so everything in there adds up to 0. We have 3 hydrogens, they're not attached to a metal, so they must be +1, so we'll say +3. So therefore the nitrogen in this instance must be -3, -3 plus 3 is equal to 0. So nitrogen in that case is -3. Let's look at nitrogen then and a nitrite ion. Okay, so again we apply the rule where the overall oxidation state is equal to the charge, which is -1. We have 2 oxygens, they're not attached to fluorine, or nor are they in a peroxide, so they are -2. So their total is -4. So therefore our nitrogen this time must be +3, because +3 minus 4 equals the -1. So nitrogen in 2 different compounds are 1 and +3, 1 and minus 3. Okay, another couple and then that'll do us. So if we look at cobalt, chloride, formula as so. Okay, so it's a complex, right? So we have cobalt, chloride. We have chlorine is -1 except when attached to oxygen and fluorine. It's attached to neither in this instance, so it's -1. Total contribution being -4. Overall charge is -2. So the cobalt therefore must be +2 because +2 minus the 4 equals the -2. So cobalt is in its +2 oxidation state. Last one then, we'll look at cobalt in what we call a complex ion again. Don't worry too much about that. Okay. So we're looking to work out what the cobalt is. So cobalt, whatever it is, plus ammonia. Okay. So we have 6 hydrogens. Okay. Each hydrogen is +1. It's not attached to a metal. So it's in its +1 oxidation state. So it's +18. Nitrogen is in its normal oxidation state here, which is -3, so that is -18. Now what we can do is the +18 and -18 can simply cancel each other out. So cobalt therefore equals the +2. So again, cobalt is in its +2 oxidation state. Okay, so that's how we work out individual oxidation numbers. We're going to have a look at these now and just check how we can use these to work out whether oxidation or redox has happened in an equation. Okay, and then we can work out what has been oxidized and what has been reduced and what is the oxidation number, or what is the oxidizing agent and what is the reducing agent. So let's first of all remind ourselves that if something is reduced, reduction means the oxidation number goes down, oxidation number goes up. So let's go through these and apply those. Chlorine is pure and uncombined, so it's 0. We don't worry about the 2 here, that's not relevant. Potassium is group 1, so it's always +1. Bromine is group 7, so it's always -1. Potassium is always +1. Chlorine is group 7, is always -1 except when attached to oxygen, but it's not. And bromine is pure bromine on its own. So that's like chlorine goes from here to there, so it's 0 to -1, so it's been reduced. Bromine, -1 to 0, so it's been oxidized. And potassium, it's just a spectator ion. So therefore that has been reduced, so it is therefore our oxidizing agent, and this has been oxidized, our bromide ions, therefore it is our reducing agent. Very simple. We could further pull the half equations out of this. So chlorine, Cl2 goes to chloride, okay, 2Cl minus. It has been oxidized, it's lost electrons, so it has lost, in this instance, 2 electrons, whereas bromide ions go to bromine. They have been reduced, they must have gained electrons, and they have gained the 2 electrons that were lost up here. Okay. Next one then, let's take our manganese dioxide with hydrochloric acid to give us manganese chloride plus chlorine plus water. Alright, so again we'll go through it and we'll put in our oxidation numbers based on the rules. So oxygen is always -2, okay, except with fluorine or a peroxide, so it's -2 here, so it's total. So it's -2 times 2, so it's total of -4. So manganese must be +4, okay. Oxygen is -2. Hydrogen is always +1 except with a group 1 metal, well it's +1 here therefore. Chlorine is -1 therefore. Chlorine here is -1 again, it's always -1 except with fluorine or oxygen, which it isn't with either of those. So it's -1 here. Chlorine's total contribution is 2 times -1 is -2. So the manganese must be +2. Chlorine is uncombined here is 0. Hydrogen is +1. Okay. Because it's not with a metal, so it's +1, and oxygen is not with fluorine, so it's always -2. So let's have a look. Manganese from here to here has gone from 4 to 2, so it's been reduced. So that must be our oxidizing agent. Okay, and chlorine, some of the chlorines from here to here, okay, have gone from -1 to 0, so they have increased, so they have been oxidized, and therefore those are my reducing agent. Okay, and that's how we would use them to work out whether or not oxidation or reduction has actually happened. Okay, I'm sure there are more questions in your notes there if you want to have a go at them. Right, the next thing we're going to look at then is taking redox half equations and building them up into full half equations and then turn them into balanced redox equations. So these are the sort of rules here that I follow. There are other ways to do this, okay, but these rules work pretty well. So the first thing we do is we balance the species. Okay, so I'll tell you what, I'll set that over there, hopefully you can read it. Okay, so let's take two half equations that the examiner might give us, and so they'll give us the bare bones. They'll say, for example, a permanganate ion goes to a manganese 2+, and they might say iron 2+ goes to iron 3+. And you've got to build these up into the full half equations, and then you've got to balance them and turn them into the full ionic equation. So that's what the examiner would start us off with. So let's see how we go from there. So we balance the species in the half equations, but we leave oxygen and hydrogen alone. Well, that means manganese here. So we've got one manganese here and one manganese here. Done. And there's only iron there, so that's actually nothing to do in this step here. We then use we then use oxygen, to balance water, to balance. We balance oxygen using water molecules. We have 4 oxygens there, so I need 4 water molecules there. We have no oxygens down here, so we don't need to worry about that. We then use hydrogen ions to balance hydrogen atoms. Well, I have 8 hydrogen atoms there, so I need 8 hydrogen ions on that side. Okay, no hydrogens down here, so I don't need to worry about that. Then I need to balance electrons using balance charges using electrons. So my total charge on this side, okay, is +7 -1 and 8. My total charge on this side is +2. So I can only use electrons, which are each one is negatively charged, to balance the charges out. So I need 5 electrons on that side. 5- and 7+ gives me 2+. Over here, I just need 1 electron on that side. +3 - 1 is +2. Then we've got to combine these two half equations together to get a full ionic equation. So you reduce the numbers of electrons in each equation to the lowest common multiple. Well, they're in a 1 and a 5, so I can't reduce them any further here. Then you multiply each equation by the number of electrons in the other equation. So I'll put my arrow down there. So there's 1 electron in here, so I've got to multiply everything on that one by 1. 5 electrons here, so I multiply everything on that by 5, and then I combine. So let's deal with the top equation first. So I have MnO4 minus just one of them, plus 8H+. Okay, down here on the left of the arrow, I have Fe2+, but I need to multiply it up by 5. So it's 5 Fe2+. Go over here, I have 1 Mn2+, plus I've got my waters, and I just multiply the 4 waters by 1. And down here I have 5 Fe3+. And that's it. That's your full ionic redox equation. You just check finally then for any waters or H pluses that are on either side. Okay, so there isn't, so I have H pluses here, I have none there. I have waters here, I have none here. If there were, for example, let's say 8H plus on that side and 3H plus on that side, I got to get rid of those, and that gets turned into a 5. Likewise, so you're just looking at the net change. If I had 3H2O on that side, and I had 10H2O on that side, okay, I get rid of the 3, and that's 10 becomes a net change of 7 waters. Okay, I'll do one more, and hopefully that will allow you guys to tackle any that come your way at A level. So let's do dichromate. Cr2O7 2- goes to chromium 3 plus ions. Okay, excuse me. And let's do copper goes to, no, we'll do copper, yeah. Let's do copper going to copper 2 plus. Wouldn't happen, but for the purpose of us, it ticks a lot of boxes here. Right, so let's go. Balance equations in each half equation, but not oxygen and hydrogen. So we ignore the oxygen, but we do have 2 chromiums here, so I need to put a 2 there. Balance oxygen using water molecules. Okay, so I have 7 oxygens there, so I need 7 waters there to get my 7 oxygens. No oxygens down here to worry about. Use hydrogen ions to balance hydrogen atoms. Well, I've got 14H plus needed there because I have 7 times 2 hydrogens. Nothing down here to worry about. And then finally I've got to balance my electrons, so I calculate my total charges. So here I have 14 pluses and 2 minus, so I've got plus 12 in total on this side. And over here I have 2 times plus 3. A lot of people always forget about that too. Okay, so I need 6 electrons there, and that makes both sides plus 6. Down here, plus 2, okay, plus 2 electrons, 0 charge here, okay, both sorted. Right, we reduce the number of electrons to the lowest common multiple, so that's 1 and that's 6, and we multiply the other equation by it, so we multiply this by 3 and we multiply this one by 1. Okay, let's put our arrow down here. Okay, so we have everything here multiplied by 1, so we have Cr2O7 2 minus plus 14H plus Cu goes to, 3Cu goes to 2Cr3 plus 7 waters plus 3 times Cu2 plus 3 of those, and that should be it. You can quickly scan your eye through it and check 7 oxygen, 14 hydrogen, 14 hydrogen, 3 copper, 2 chromium, and the charges should be balanced out as well. Hopefully that's a brief overview, guys, of how we calculate oxidation states and then use those to work out whether oxidation reduction has or hasn't happened, and allow us to identify the oxidizing agent and the reducing agent, and then finally how we write our ionic half equations and turn those into full ionic equations. I think if you can do all of those in the video, guys, you shouldn't really have any particular issues with what crops up at air levels. Obviously you'll get unfamiliar equations and reactants, but you just have to deal with those whenever when they arrive in the equation. The last thing I didn't check there was there any hydrogen ions in excess on either side or waters, and there isn't. Okay, right, so hope that helps. Any questions, please see me.